Have you ever wondered what's really going on inside the wires of your phone or your laptop? We tend to think of electricity as this super complex technical thing. But today, we're going to pull back the curtain and look at its secret life. We're going to see it not as some dry physics lesson, but as what it really is, a story. A story about energy, a mission, and a pretty epic journey. So, yeah, what if we just told the story of a circuit? Instead of talking about abstract forces and electrons, what if we had a hero on an epic quest? Well, that's exactly what we're going to do. It's the best way to really get a handle on the fundamentals of DC circuits. And here he is. Let's meet our hero. We'll call him Mr. Coulomb. Now, he represents a single unit of electrical charge. He might look small, but trust me, he's the main character in our story, the little guy responsible for getting all the work done in the entire electrical world. So what's his deal? Well, Mr. Coulomb has one very specific job. He's basically an energy delivery guy. His whole purpose in life is to pick up a bundle of electrical energy from a source, hoof it along a path, and drop it off wherever it's needed. And this right here, this is his delivery route. The circuit is his entire world. He starts at the battery, that's kind of like his warehouse. He picks up his energy packet, and then he delivers it to the light bulb to make it shine. Then, totally empty-handed, he travels right back to the battery to do the whole thing all over again. It's a continuous loop. Okay, so let's zoom in on the two most important moments in Mr. Coulomb's day, picking up the energy package and then dropping it off. This, right here, is the heart of the whole story, what we'll call the Great Energy Exchange. So, you might be asking, how does Mr. Coulomb get all this energy? Well, inside the battery, there's this chemical reaction that acts like a powerful slingshot. It gives our little hero, who's tired and out of energy, this massive kick, loading him right back up with a fresh bundle of energy for his next trip. Now, this kick actually has a formal name, electromotive force, or EMF for short. But here's a heads up. The word force here is a little misleading. It's not a force like a push or a pull. It's way better to think of it as the total amount of energy the battery gives to each and every Mr. Coulomb that passes through. It's his total energy budget for the entire journey. So here's the key thing you gotta remember. The difference between the energy Mr. Coulomb gets and the energy he gives away. The EMF is the total energy he gets from the battery. The potential difference, or PD, is the energy he drops off or uses when he passes through something, like our light bulb. It's really just supply versus demand. Here's the simplest way to keep it straight in your head. The energy gain, the EMF, that all happens inside the source, inside the battery. The energy drop-off, the potential difference, that happens out in the circuit, at the light bulb. It's just pick-up versus drop-off. Simple as that. But here's the twist in our story. Because in the real world, the journey is never perfect. The battery isn't some magical, 100% efficient energy warehouse. Nope, it has a hidden cost, something we can think of as a little internal tax. Okay, so let's look at what's really going on. Every real-world battery has this tiny hidden resistor inside of it. You can see it here labeled with a little r. It's just an unavoidable part of how batteries are made. This is what we call internal resistance. It's just a little bit of opposition that exists right there inside the battery. And because of it, Mr. Coulomb has to spend a tiny bit of his energy just to fight his way out of the battery. It's literally an energy tax that the battery takes for itself before he can even start his main delivery. And here's why that's a big deal. Because of that internal tax, the energy Mr. Coulomb has left for his delivery is always a little bit less than what he started with. And that means the potential difference available to the light bulb is always less than the battery's total EMF. All right, theory is great and all, but let's see how this stuff actually plays out. It's time to use what we've learned to become electrical detectives and solve a little puzzle. So here is our crime scene. A circuit with 3 lamps, we'll call them A, B, and C, and 3 switches to control them. Looks simple enough, right? But there's a problem. We know for a fact that one of these lamps is broken, so our mission, should we choose to accept it, is to figure out which one it is. And our only tool is an ohm meter, which just measures resistance. Basically, it tells us how hard the path is for Mr. Coulomb. So how can we use it to find the faulty lamp? Okay, here's our evidence log. We start testing the circuit by flipping the switches in different combinations. Now, notice, when we test the path through lamp B or lamp C, we get these normal resistance readings, 15 and 30 ohms. Those are clear paths. Mr. Coulomb can get through. But look at that first reading. When we try to test the path through lamp A, the meter reads infinity. And infinite resistance means there's a total, complete break in the path. For Mr. Coulomb, that's a dead end. And that infinity reading, that's our smoking gun. It tells us without a doubt that the path through lamp A is completely broken. The little filament inside the bulb must have snapped. Case closed. The faulty lamp is A. So, puzzle solved. But let's zoom out for a second. Why does this whole story about Mr. Coulomb and his little energy tax actually matter to you? Let's just wrap up the whole story nice and neat. The EMF, that's the total energy a brand new battery promises it can deliver. The internal resistance, well, that's the little bit of energy the battery keeps for itself, that internal tax. And the potential difference, that is the actual usable energy your device gets to play with. And look, this isn't just some fun story we made up. This is the fundamental principle behind every single battery-powered thing you own. Your phone, your earbuds, your TV remote, a flashlight. They all operate on this exact cycle of energy gain, energy loss, and that pesky, unavoidable internal tax. And that kind of leaves us with one last thought. This idea of an internal tax, losing a bit of energy just to get started, it doesn't just happen in circuits. Think about it. Where else in your life do you have to pay a small price, lose a little energy, just to overcome the friction of starting something new?